We're going to continue with the hospital performance example and now consider the case when a hospital wants to assess the impact of both nurse communication and hospital level on the percentage of patients who would always recommend the hospital. Go ahead and open up the hospital data dataset in Stata and we'll get started with the multiple linear regression example. The first thing we want to do is make a scatter plot of the outcome versus the new covariate. The outcome again is recommend yes, and the new x variable or the new covariate that we're going to look at is quiet always. This is an indicator of the percent of patients who said that a hospital was always quiet. So examining this scatter plot, it looks like maybe we could draw some line through this for a linear relationship between the covariate and the outcome. Also, if we were fitting a simple linear regression model, we might see a little bit of a violation of homoscedasticity here. It looks like maybe the variance is a little bit bigger out here and the variance gets smaller as the percentage grows. But we're not looking at a simple linear regression model. Now we're doing multiple linear regression. So we're looking at the impact of quiet always on the outcome recommend yes, but we're looking at it conditional on the covariate we've already looked at, nurse always. So let's go ahead and write down the exact model that we're going to be fitting. Our outcome for hospital I, where I equals 1 to n, so we have n different hospitals. Our outcome yi for hospital I is defined as the percent of patients who recommend the hospital always. Now we need to consider the model covariates. We have two covariates. The first covariate we're going to denote x1 sub I, and this is the same covariate from the previous tutorial. It's just the percent of patients in hospital I who say that their nurse always communicated well. And now we're adding an additional covariate into our linear regression model, x2. It's defined as the percent of patients who report that hospital I is always quiet. So we can write down our multiple linear regression model as yi is equal to an intercept alpha plus beta 1 times x1 plus beta 2 times x2 plus some residual error, where we model that residual error as following a normal distribution with mean 0 and variance sigma squared. As we've seen in the previous tutorials, we could alternatively write this model as the mean mu of yi given x1 and x2 is equal to alpha plus beta 1 x1 plus beta 2 x2. And we could say that yi given x1 and x2 follows a normal distribution with mean equal to this mu and variance sigma squared. So this sigma squared, those guys are equivalent. These are exactly the same model. Now that we've written down our multiple linear regression model, let's go ahead and fit this model in Stata. Fitting a linear regression or a multiple linear regression model is the same as fitting a simple linear regression model in Stata. We just go statistics, linear models and related, and then click on linear regression. The only difference is now we have more than one independent variable. So for my independent variables, I select nurse always and quiet always and hit submit. Now let's look at the output of our linear regression model. The constant corresponds to alpha. Nurse always is going to be beta 1 and quiet always is beta 2. So I can write down my fitted regression model as yi is equal to alpha, or negative 18.6, plus beta 1, 1.13 times x1, plus beta 2, 0.02 times x2, plus some residual error. And I estimate that this residual error follows a normal distribution with mean 0 and variance equal to 7.28 squared. Let's go ahead and look at the interpretation of our coefficients. First, we have beta 1. We estimate that beta 1 is equal to 1.13 with 95% confidence interval from 1.08 to 1.19. And we can interpret beta 1 hat as for a 1% increase in the percent of patients who say that the nurses always communicate well, we see on average a 1.13% increase in the percent of patients who would always recommend the hospital when the percent of patients who say the hospital is always quiet is fixed. So remember, when we have this multiple linear regression model, we have to interpret our coefficients conditional on the value of the other covariates. So we condition on quiet always, and we look at the impact of nurse always on the outcome. Similarly, we can look at beta 2. We could say that we estimate that beta 2 is equal to 0.02 with a 95% confidence interval from about negative 0.01 to 0.05. And we can interpret beta 2, or our estimate of beta 2, as for a 1% increase in the percent of patients who say the hospital is always quiet, we see on average a 0.02% increase in the percent of patients who would always recommend the hospital when we fix the percent of patients who say that their nurse has always communicated well. Last, let's look at the interpretation of alpha. The estimate of alpha is negative 18.6, and there's also a 95% confidence interval for alpha over here. Now, alpha is technically defined as the expected value, or the estimated expected value of the outcome when the covariates are both set to 0. So we would need x1 equals 0 and x2 equals 0. Now, when I summarize the covariates, I see that nurse always never drops below 48% and quiet always never drops below 30%. And therefore, alpha really doesn't have a meaningful interpretation for this study. And we know that it's not meaningful because it's negative. So it's the expected value of y when the covariates are set to 0. But we know that our outcome is a percent. So it doesn't make sense to have this negative percent. You can't have negative percent of patients recommending our hospital. So it really makes absolutely no sense to interpret the intercept in this case because we're extrapolating beyond the range of our data. Once you fit a model, it's very important to go ahead and evaluate the model assumptions. The model assumptions for linear regression are a little bit less straightforward to interpret in the multiple regression case, but we can still do it. One of the first things we can look at is this adjusted R-squared. So we can compare the adjusted R-squared for this multiple linear regression model to the simple linear regression when we didn't include quiet always, and we can see if we've improved our model fit. In fact, in the simple linear regression model, the R-squared was pretty close to what we have here. It was actually also estimated as 0.43. So it doesn't seem like we're really gaining very much or explaining much more variability in the outcome by adding quiet always into our model. Additionally, we can make some residual plots. To make a residual plot in Stata, we've seen this in the previous linear regression modules. We just go to regression diagnostics, and we'll look at a residual versus fitted plot. So the key thing to look for in the residual plot is trends. This seems to have mean 0. The variance seems to be pretty constant, so this suggests that homoscedasticity is probably a reasonable assumption, at least looking at this plot. If you see some major trends in your residuals, you might want to second guess your assumptions and see if you can add in any covariates, etc., to try to improve the fit of your model and better meet the assumptions of linear regression. So that was a plot of the fitted values versus the residuals. We can also make plots of covariates versus the residuals by doing a residual versus predictor plot. And we'll look at the independent variable nurse always first. And again, we don't see any major trends in this residual plot. We can look at quiet always as well. And as long as you don't see any blatant trends in your residual plots, usually it's okay to make to assume that the assumptions of linear regression are met as far as homoscedasticity goes and conditional normality. Also, if we saw any trends in the residual plots, this might be due to a violation of the linearity assumption. So maybe we would need to model our covariates in a more complex manner rather than just making this linearity assumption. All right, now let's say that we had a new hospital where the percentage of nurses who always communicate well is 90%, and the percentage of those who say the hospital is always quiet is 70%. We can use our linear regression model to predict the expected percent of patients who would always recommend the hospital. Now we're looking at an average here. We want to know what is the expected value of the outcome y when x1 is equal to 90 and x2 is equal to 70. So we're trying to predict the expected value. To do that, we can use that lincom command that we saw in the previous tutorial. To do that, we can use the lincom command. So it would be alpha or underscore constant plus nurse always, which is beta 1, times the value of x1, which is 90, plus quiet always times the value of x2 for this new hospital, which is 70. Using lincom, I can estimate this expected value, and it's 85.1, and I can obtain a 95% confidence interval for the expected value. Remember, we're dealing with the expected value, or the average. If I wanted to make a new prediction, so if I wanted to predict what I thought the percent of patients who would recommend this hospital would be, remember from the last tutorial, we saw that we can't use this 95% confidence interval. If we wanted the prediction for a new observation, we would have to take into account the standard error of the mean, the variance of the mean, as well as that residual variability that's quantified using that sigma squared. So it's the amount of residual error for the hospitals. So in this example, we're only interested in the expected value, so I can just go ahead and directly use this confidence interval. But make sure you understand the difference between predicting an expected value and predicting a new observation. The next thing we want to do is use our regression model to perform a couple hypothesis tests. The first thing that I want to test is that beta 1 is the null hypothesis that beta 1 is equal to 0. Essentially what I'm testing here is that there's no evidence of a linear relationship between nurse always and the outcome recommend yes, conditional on quiet always. So it's that there's no evidence of linearity conditional on the other covariates. Versus the alternative that there is some evidence of a linear relationship between nurse always and recommend yes, conditional on quiet always. To perform this test, I can just look at the regression output. Now the regression output gives us all the information we would need to know about beta 1 hat. The estimate of the coefficient is 1.13 with standard error 0.03. This leads us to a t-statistic of 40.1. And we know that under the null hypothesis, this test statistic follows a t-distribution with the number of degrees of freedom equal to the sample size minus the number of covariates in the model, which is 2, minus 1. So our degrees of freedom is 3,567. Using this distribution, I find that my p-value is less than 0.001, and therefore I would reject the null. And I would conclude that we have evidence that an increase in the percent of patients who say that nurses always communicate well results in an increase in the percent of patients who would always recommend the hospital on average, fixing the percent of patients who say that the hospital is always quiet. So the interpretation is a little bit awkward. Get used to interpreting these conditional averages. The next thing we want to test is whether beta 2 is equal to 0. Now we're testing for no evidence of a linear relationship between quiet always and the outcome recommend yes when we condition on nurse always. So we're looking at beta 2 hat here. The estimated coefficient is 0.02 with a standard error of approximately 0.02. We end up with a test statistic, t, is equal to 1.5. Again, under the null hypothesis, we know that this test statistic follows a t-distribution with 3,567 degrees of freedom, and we end up with a p-value that's equal to 0.14. So in this case, we fail to reject the null hypothesis and conclude that we don't have enough evidence in the data to say that an increase in the percent of patients who say that a hospital is always quiet is linearly related to the percent of patients who recommend the hospital always on average, fixing the percent of patients who say that nurses always communicate well. Now, if I do a bunch of these univariate hypothesis tests, I can run into problems with multiple comparisons. Another test that I could do is I could jointly test whether both beta 1 and beta 2 are equal to 0. Versus the alternative hypothesis that at least one of beta 1 or beta 2 is not equal to 0. I can't directly perform this hypothesis test using the output of the linear regression. So now I have to try this new command in Stata, which is called test. So after I've run a regression model in Stata, I can use the test command. And I can say test nurse always and quiet always. And what that's going to do is, Stata tells you right here, it's testing the null hypothesis that both nurse always equals 0 and quiet always is equal to 0. Now we can see down here that to do this hypothesis test, we need to calculate an F statistic. This F statistic is equal to 1,363.4. Now, under the null hypothesis, Stata tells you that this test statistic follows an F distribution with 2 numerator degrees of freedom and 3,567 denominator degrees of freedom. So using that null distribution, we find that the p-value is less than 0.001. So we do have evidence that at least one of beta 1 or beta 2 is non-zero. Now the last thing I want to look at in this exercise is, do we observe any collinearity between our two covariates, x1 and x2? And how does this impact our results? So thus far we've only looked at the relationship between the covariates and the outcome. But if I were to make a scatter plot, let's go ahead and do that. Make a scatter plot of the y variable is nurse always, and the x variable is quiet always. Let's think about how are these two covariates related to each other? And when we look at this plot, we actually see that it looks like there's a linear relationship between nurse always and quiet always. So this is evidence of collinearity. And this occurs when you have two covariates that are highly correlated. The question is, how does this impact the results of our regression model? Just as a quick example, suppose I were to instead fit a simple linear regression model with recommend yes as my outcome and quiet always as my covariate. We now see that in this simple linear regression model, that quiet always is highly associated with the outcome recommend yes. So it does appear that when you exclude nurse always from the regression model, quiet always is linearly related to the outcome recommend yes. However, we saw that when you add nurse always into the regression equation, the coefficient for quiet always is now much smaller, and when we did the hypothesis test, we saw that once you condition on nurse always, there's no evidence of a linear relationship between quiet always and the outcome. So this is a classic example of collinearity, where we see an association between a covariate in a simple linear regression model, but when we add in another covariate, this covariate is no longer significant because of the high correlation between nurse always and quiet always.